Good morning, respected jury members and faculty. My name is Kothari Samyak Dharmendra, student code PCM 24330, and I am presenting my directed research project for the MTech in Construction Engineering and Management program at SEPT University, Spring 2026. The title of my research is 5S Implementation in Construction Site Stores. The study has been carried out under the guidance of Mr. Manish Dave. At the heart of this research is one fundamental question: construction sites spend enormous effort planning schedules, budgets, and quality. But how much structured attention do we actually give to the site store? That space where materials are received, stacked, issued, and tracked every single day. My research attempts to answer that question by applying the 5S Lean methodology to construct site store across five live high-rise projects in Ahmedabad and Gandhinagar. I will walk you through the observation, audit findings, survey analysis, and a practical framework developed from this work. With that introduction, let me take you through the structure of this presentation. These slides presents the six-chapter flow of the presentation. We begin with chapter 1, Study Brief, covering the background and the need for this study. Chapter 2 is the research framework, covering the aim, objectives, scope, literature review, research gap, and methodology. Chapter 3 is data collection, which includes project details, site logistic plans across five projects, and the as-is 5S observation. Chapter 4 is the audit and survey, where we look at the 5S audit checklist, scoring, and the 60 respondent industry survey. Chapter 5 is the analysis, a detailed pillar-wise examination of all 5S elements. And chapter 6 is the framework and recommendation, where we bring everything together into a practical implementation model, corrective actions, and the conclusion. This narrative follows the clear research story from problem identification all the way to a framework that practitioners can actually use on site. This slide captures the essence of the entire study in one place. The research examines persistent inefficiency in construction site stores of high-rise residential and commercial projects across Ahmedabad and Gandhinagar. The focus is on the 5S Lean methodology: sort, set in order, shine, standardize, and sustain, and its applicability to improve material organization, safety, and productivity. The study was conducted across five live high-rise projects ranging from G plus 26 to G plus 37 floors, both residential and commercial types, during February to March 2026. The data collection involved direct site observation, photographic documentation, comparison of plan versus actual site logistics, a structure 5S audit of 38 parameters, and a 60 respondent industry survey using a 17-item Likert scale questionnaire. The headline finding is this: the overall 5S implementation score across five sites stands at 62.21%, indicating moderate adoption. But the more concerning finding is within that average standardized scored only 45.56% and sustained scored just 42.33%. These two pillars are not knowledge gaps, they are systemic and cultural gaps. Materials constitute 50 to 60% of total project cost. The site store is the critical interface between procurement and execution, and yet it is the most under structured part of construction site management. This study attempts to change that. Let me put the construction industry context on the table. Materials account for 50 to 60% of total project cost. That single fact makes material handling one of the most cost critical activities on any construction site. Yet, despite this, the site store, the very place where all materials are received, stored, and issued, operates without any structured management system in most projects. The site store is meant to be the interface between procurement and execution, but in reality, we observe is very different. Stores evolve organically rather than systematically. Layouts develop through ad hoc decisions. Materials are stacked wherever space is available. Workers spend excessive time locating materials, not because they are absent, but because no one knows exactly where they are. This hidden inefficiency accumulates over time. It is not a single visible event. It is a cumulative cost across trades, shifts, and the entire project life cycle. The safety dimension is equally serious. Clustered storage areas, blocked pathways, improper stacking of heavy materials. These are not just housekeeping issues. They are active safety hazards on a risk construction site. And there is a sustainability concern too. Poor storage increases material damage, deterioration, and waste, directly conflicting with the sustainability goals that project now aspires to meet. These six interconnected problems, material searching time, damage and pilferage, unsafe conditions, space inefficiency, absence of visual controls, and the gap between planned and actual logistics, form the foundation of the problem statement for this study. Construction site stores lack structured system for organization and management, leading to inefficiencies in material handling, reduced productivity, increased waste, and compromised safety. The aim of this study is to investigate the application of FIS methodology in construction site stores and evaluate its potential to improve organization, efficiency, safety, and material management practices in high-rise residential and commercial projects. The five objectives guide the research progressively. The first objective is to examine existing site store practices. The second is to identify good and bad best practices through the site observations and logistic plans comparison. The third is to evaluate the level of implementation through the audit scoring and survey percentages. The fourth is to identify parameters falling below 75% and convert them into targeted improvement action. And the fifth is to develop a practical 5S implementation framework specifically for high-rise projects above 120 meter. The scope is clearly defined: high-rise residential and commercial projects in Ahmedabad and Gandhinagar. Material types include steel, cement tiles, formwork, MEP, and consumable, all 5S pillars, and both visual management and site logistic aspect. It is equally important to state what this study does not cover. The sector is limited to all high-rise buildings only. The scope is restricted to site stores, not the entire supply chain. The study covers five projects, so findings are not a nationwide census. Observations were time-bound to February and March 2026. And the survey of 60 respondents provides strong industry perspective, but it is not an exhaustive data set. These limitations are not weakness. They are the honest boundaries within which the findings can be trusted. The literature review was organized across 13 thematic areas. Let me highlight the most significant ones for this study. On lean in construction, Manipur et 2022 confirmed that non-value adding activities are widespread in fragmented construction projects and lean adoption remains particularly uneven in small and medium enterprises. This provides the macro context for why 5S is needed. On the 5S conceptual framework itself, Singh and Singh Ahuja 2015 positioned 5S as a foundational lean tool requiring minimal investment and the entry point for continuous improvement culture. On the productivity, Al Amin 2019 and Oja 2023 demonstrate that organized workspaces measurably reduce search time and improve cycle time even through partial 5S implementation. On safety, SML 2025 report a 53% reduction in workplace risk levels post 5S in the woodworking industry, a compelling number that translates directly through construction site. On warehouse and inventory management, Rizek 2021 and Firdos and Vidija 2019 show how proper labeling at defined zones and visual management reduce retrieval time findings directly transferable to construction site store. On challenges, Minimally 2022 identify lack of worker training, dynamic site conditions, and absence of practical framework as the primary barriers to the sustainable 5S adoption. Themes that my research directly validates. The literature clearly established 5S as a proven adaptable low-cost tool, but it also confirms that focused application to construction site stores remains largely unexplored, which is exactly where this research steps in. While 5S is well established in manufacturing, healthcare, and warehouse settings, its focused application specifically to construction site material store remains largely unexplored, particularly in Indian high-rise construction context. I identified six distinct research gaps. The first is industry focus. Most 5S study concentrate on manufacturing, jute, mining, casting, and pharmaceutical industry. Construction site stores are rarely the primary research subject. The second gap is store specificity. Existing construction studies addresses general site store practices like scheduling and quality, but store-specific application zoning, labeling, FIFO control are under-documented. The third gap is an integrated approach. No existing study combines 5S with site logistic evaluation, material management, inventory control, and audit scoring all within a single research framework. The fourth gap is about dynamic environments. There are very few frameworks designed for implementing 5S in temporary, continuously evolving construction conditions, where fixed systems simply cannot hold 5S in temporary, continuously evolving construction conditions, where fixed system cannot hold. The fifth gap is the Indian context. Cultural, contractual, and site-specific dynamics in India differ significantly from the Western context that dominate existing literature. And the sixth is sustainability outcomes. Few study explores the long-term relationship between sustained 5S and waste reduction in site store. This study bridges all six gaps. It examines 5S in live construction site stores, combines logistic comparison, audit scoring, and a 60 respondent survey, and produces a practical implementation framework for high-rise projects exceeding 120 meters. The methodology is built around three research questions. First, what are the existing material storage practices in construction sites of all residential projects? Second, which element of 5S are most relevant to construction site stores and can be 5S be adapted to dynamic and temporary site? Third, what improvements can be expected through 5S implementation and what challenges may affect its sustainability? The research type is applied and descriptive. A qualitative case study approach with observational analysis, which is a well-established methodology in a lean construction research. The study area covers 5 high-rise construction site material stores in Ahmedabad and Gandhinagar observed from February 9 to March 31, 2026. Data was collected through four complementary methods: direct site observation and photographic documentation, comparison of plan versus actual site logistic plans, a structured 5S audit checklist of 38 parameters using yes or no scoring, and a 60 respondent industry survey via Google Form with 17 Likert scale statements and open-ended questions. The analysis technique combines qualitative observation with quantitative scoring. The scoring formula is straightforward. Pi percentage equals the obtained mean score divided by 5 multiplied by 100. Looking at the audit scoring format, sort as 6 parameters, set in order as 15, shine as 9, standardize as 4, and sustain as 4, totaling 38 parameters. The observed overall score came to 22 out of 38, which is 58%, a grade C. The outcome of this methodology is the identification of improvement areas and the development of a practical 5S implementation framework for high-rise construction site stores. This workflow diagram shows the 10 steps of the research process in sequence. It begins with step 1, problem identification, where gaps in construction site store management were confirmed through preliminary observations. Step 2 is the literature review covering 5S principle, lean construction, warehouse management, and material management in construction. Step 3 is data collection through site visits conducted across all 5 projects from February to March 2026 with photographic records and discussion with site personnel. Step 4 is the site logistic plan comparison, comparing the initial versus actual logistic plan for each project to identify deviations and adaptations. Step 5 is the 5S as is observation, categorizing good and bad practices across all 5 pillars. Step 6 is the 5S audit using the 38 parameter checklist across all 5 pillars. Step 7 is the industry survey, 60 valid respond using 70 Likert scale statements. Step 8 is data analysis and pillar scoring, calculating mean score, 5S percentages, and identifying gaps below 75%. Step 9 is framework development, the 5S implementation framework for project above 120 meters, and step 10 is conclusion and recommendation, synthesizing all findings into practical outputs. The 5 projects studied span 2 cities, 2 project types, and 4 different building configuration deliberately chosen for this diversity. Project 1 is a residential development in Ahmedabad, 3 basement plus ground plus 37 floors. Key store areas include Maiwan materials, MEP, steel, and cement. Project 2 is also residential in Ahmedabad, 38 plus G plus 35 floors with Maivan material, tiles, cement and general store. Project 3 is a commercial project in Gandhinagar, 4 basement plus ground plus 28 floor, focused on steel racks, cutting and bending operation. Project 4 is residential in Gandhinagar, 3 basement plus G plus 28 floors with firefighting store, plumbing, sand and steel area. Project 5 is commercial in Gandhinagar, 3 basement ground plus 26 floors with formwork yard, store and scrap yard. All five initial logistic plans were created between May 2024 and July 2025 and the current status was recorded on 28 March 2026, allowing a meaningful comparison of planned intent versus actual execution. The purpose of selecting multiple projects with varying scale, type and location is important. If I had studied only one project, the findings could be dismissed as site specific. But by studying five diverse projects and finding consistent patterns across all of them, the finding gains credibility and generalizability. The study focused on six areas within each project: materials, storage methods, layouts and space utilization, accessibility, housekeeping standards, inventory visibility, and safety conditions. Project 1 is the largest in this study, a 37-story residential tower in Ahmedabad. Looking at the initial logistic plan dated June 2025, the design intention was clear and structured. Designated storage zones were provided for key materials: steel yard, cement store, Maivan store with 8-meter vehicle access routes and 2-meter safe pedestrian passages. A safety park and scrap zone were pre-planned. Now, when we compare this with the actual site condition recorded in March 2026, we see significant deviation. Maivan materials have expanded and are now blocking MEP store access. Steel stored in basement 2 is practically inaccessible. Sand and aggregates are stored without any segregation. The driveway gets blocked during concrete pumping operation. Materials have even spilled outside the site premises. Integrating this through the 5S lens, sort is violated. Reinforcement scrap is mixed with general waste with no designated scrap zone. Set-in order is violated with the MEP store is blocked. Shine is compromised. Pathways are dirty and obstructed. Standardize is absent. There are no visual controls for material identification and sustain is non-existent. No monitoring or audits are being conducted. This is not a failure of the initial plan. The plan was well conceived. It is a failure to update and enforce the plan as construction progress. That gap between planning intent and execution reality is a primary driver of site story inefficiency. Project 2 is the strongest performer in this study from a 5S compliance standpoint. The initial logistic plan from August 2024 was excellent. A 115 square meter central store was clearly segregated zones for cement, block adhesive, Maivan and tiles. A QA/QC lab and cube testing zones were integrated into the layout. Well-defined circulation paths were maintained around the core. Administrative and operational zones were clearly separated. By March 2026, the actual condition shows a meaningful evolution rather than a breakdown. Storage zones are more defined and aligned with actual operations. Tiles are stored batchwise to prevent shade variation during installation. Steel scrap is cordoned with a green net near the steel yard, making it accessible for reuse in lintel, coping, and mullion work. The QA/QC lab is now more accessible than in the initial plan. The 5S reading on this project is much stronger. Under short tiles scrap is separately stored because cut tiles are sharp and represent an injury risk, a genuine safety aware practice. Under set-in order, tiles stored batchwise shows operational thinking. Under shine, material tagging has been introduced and maintained. Under standardization, GRN records are kept even though a formal SOP is absent. Under sustain 5S, housekeeping inspection is conducted periodically with the safety team. Project 3 is the only commercial project in Gandhinagar studied at the 4 basement plus 28 floor scale. The initial plan from January 2025 was well structured: 8-meter ramp with 9-meter turning radius, 2-meter safe pedestrian passages, designated steel racks, threading machine, and systematic placement of sump pumps. A safety park and scrapyard were pre-planned. By March 2026, the actual layout shows purposeful evaluation rather than breakdown. Double steel rack the arrangements have been added to manage higher steel inflow. Cutting, bending, and threading machines are consolidated into an activity cluster. A temporary crane zone and boom pumping areas have been introduced. The steel yard area and canteen facilities are clean and maintained. However, the short gap is visible. Different steel types are stored together. Operational consolidation has improved workflow but reduced clarity in material segregation. Steel racking labeling is present and represents a partially standardized practice, but there is no formal 5S audit system. Practices depend heavily on supervision. The key inference from this project is that commercial site tends to manage material flow well due to higher volume discipline, but the absence of formal documentation and audit system makes improvements person dependent rather than system dependent. Project 4 is a residential project in Gandhinagar, 3 basement plus 28 floors, and it demonstrates some of the most encouraging individual site practice observed in this study. The initial plan from May 24 placed the store centrally near the entry for easy unloading with the steel yard towards the upper periphery and clear access route throughout. By March 2026, materials are categorized by type: firefighting stove, plumbing, shuttering, sand, though they are clustered rather than strictly segregated. A debris chute has been introduced for finishing stage wastage. The steel scrap yard has expanded due to higher turnover. The specific practices worth highlighting are scaffolding components are stored and segregated size-wise, an excellent area and sit-on practice. Steel scrap is cordoned with a green net and designated for reuse. Cement storage is enclosed and moisture protected. And importantly, material tagging with category-wise codes has been introduced and maintained. A secret to practice. The 5S inspection is conducted by the safety and store team periodically, a sign of status quo taking root even if not yet formalized. Project 4 shows that individual practices can be strong even without a formal 5S framework, but it also illustrates the ceiling that informal implementation hits without written SOPs and structured audits. Project 5 is the second commercial site, 3 basement plus 26 floors in Gandhinagar, and it presents a mixed compliance picture. The initial plan from May 2025 was structured steel yard along the upper edge, homework yard, store and labor rest areas on the periphery, curing tanks and scrap yard plant, and building footprint kept clear for construction activity. By March 2026, storage and activity zones have been reorganized for execution. Homework yard has shifted closer to execution areas, and here is one of the best practice observed across the study. Scaffolding is neatly stacked by type and size. A worker can walk in, identify what they need, and retrieve it without confusion or double handling. However, the short gap is present. Props of different types are stored together without identification. There is no visible SOP on site. Arrangements are person dependent, and there has been no formal fire training or audit observed. The scaffolding practice in Project 5 proves something important. Good individual practice do exist on these sites. Workers and supervisors can get it right. What is missing? The system that ensure it stays right consistently, not just when someone personally cares about it. This comparative table summarizes the 5 project logistic analysis. Looking at the column, Project 1 had a good initial plan but a low actual compliance with the MEP access blockage as the key issue and a reactive layout evaluation. Project 2 had an excellent initial plan and moderate to high actual compliance, the strongest performer. Project 3 had a good initial plan and moderate compliance with steel segregation as the key issue. Project 4 had a good initial plan and moderate to high compliance with material clustering as the challenge. Project 5 had a moderate initial plan and low compliance with props being stored without differentiation. Across all 5 projects, the good practice that stand out are material tagging and FIFO in projects 1 and 2, tile batch control and steel scrap netting in project 2. Steel rack is labeling in project 3, scaffolding order and tagging in project 4, and scaffolding stacking in project 5. The broader inference from looking at all 5 projects together is at the initial stage, logistic layouts are well organized. As the construction progresses, layout adapt to practical needs, activity-based zoning take over. In advanced stage, arrangements become dynamic and responsive but may lead to clustering, reduced clarity and congestion. The critical finding is that no project fully maintained its initial logistic plan, not one. This confirms that the gap between planned and actual logistic is a systemic issue, not a site-specific anomaly. It is a primary driver of store inefficiency. This finding directly supports the need for a continuous logistic management protocol alongside 5S implementation, which is addressed in the framework I will present later. During my site visit from February to March 26, I documented 8 categories of good practices that I want to highlight. The first is material tagging and category coding observed in Project 1 and 2 and 4. Materials are assigned category-wise codes for systematic traceability. This touches three pillars simultaneously: sort, set in order, and standardize, because tagging eliminates ambiguity at the most basic level. Second is steel stacking diameter wise observed in project 1, 2, and 3. Reinforcement bars are stacked by diameter 8 mm, 10 mm, 12 mm, 16 mm, 20 mm, and above, elevated above ground level to protect from corrosion. This is a strong sit-on practice. A worker can identify what they need visually without calling anyone. Third is cement storage with FIFO observed in project 1, 2, and 4. Cement bags are stacked in enclosed areas to protect from moisture, and the FIFO system is followed. Older stock is issued first. This prevents deterioration and supports inventory control. Fourth is liquid material storage on rack system. Project 1 and 2, diesel, shutting oil, grease, and lubricants are stored in fully enclosed segregated areas without proper identification, spill control, and regular cleaning. This is both sit-on and CISO, and it directly prevents fire hazard. Fifth is steel stirrup waste sorted and reused. Project 1 and 4, cut stirrups which could easily be dismissed as scrap are reviewed, straightened, and reused where applicable. This is theory in action, separating usable material from actual waste, and it documents a habit of resource consciousness. Sixth is scaffolding stored by type and size. Project 4 and 5. This was the single clearest example of sit-on I observed across the study. Workers can identify and retrieve components without confusion. Seventh is steel scrap cordon with green net. Project 2 and 4. Reusable steel scrap is separated and designated for specific reuse activities like coping, lintel work. This is sort and set in order working together. And eighth is batch-wise tile storage. Project 2. Tiles are stored by size, batch, and type, with scrap tiles stored separately. This prevents shade variation during installation, a direct quality benefit, and reflects both standardized and sort. For every good practice observed, there were multiple bad practices. Let me walk through 8 major categories. First, Maven materials stored with no passage and no identification observed in Project 1 and 5. Props of different types and sizes are stored together without any identification or clear eye. The result is blocked movement, handling difficulties, and impossible inventory tracking. A worker cannot retrieve what they need without physically dismantling the stack. Second, waste blocking access. Project 1 improperly place scrap obstructs access, creates movement restriction and is a direct safety hazard. This is not a small inconvenience. This is a set in order violation with safety consequences. Third, reinforcement scrap mixed with general waste. Project 1 steel scrap of different types is stored randomly with no designated area. Access is restricted. The material is difficult to remove. Congestion, material loss, and tracking failures result. Fourth, tile storage with space constraints and no batch arrangement. Project 1 tiles are stacked size but no batchware. Inner tiles are accessible without disturbing the entire stack. This leads to double handling, shade variation risk, and reconciliation difficulties. Fifth, sand and aggregates mixed with no zone definition. Projects 1, 2, and 4 sands and aggregates are stored together as receipt without segregation. They are later shifted to separate locations, resulting in double handling, contamination, and quality risk. This violates sort, set in order, and standardized simultaneously. 6. Mixed debris waste at multiple locations. Project 1 and 4. Concrete, tiles, steel, and packaging waste are dumped together without segregation. No defined waste collection area. Exit disposal becomes difficult and safety risk increases. Seventh, reinforcement of different sizes stored together. Project 1 and 3, column steel, beam steel, and slab steel. Different cutting lengths and diameters are stored together without identification. Wrong material gets issued. Handling time increases. Reconciliation error occurs. And 8, driveway and pathway blockage. Project 1, the driveway is blocked by the concrete pump during concreting. The pathway to the site office is blocked by scattered materials. These are not occasional events. They represent the absence of a defined traffic and access management system within the site store. The 5S audit was conducted using a structured checklist of 38 parameters covering all 5 pillars. Each parameter was evaluated on a yes 1 point and no 0 point basis. The total possible score was 38. The SS store achieved 22 points, resulting in overall compliance across of 58%. The assessment was conducted through physical verification, visual inspection, and interaction with store personnel. that may highlight the key gaps identified across each pillar. Under sort 6 parameter, discarded scrap tools and PPE are not identified or stored properly. The corrective action is to create designated scrap zones with labeled bins and include it in the SOP. Expired, damaged, or unused materials are not removed from shelves. A monthly rack inspection schedule is recommended. Under set in order 15 parameters, safe vehicle access for material delivery is not reliable. Maintained. Floor markings for walkways and storage areas are absent. Color-coded demarcation is needed. Sample items are not labeled zone. Directional signages for entry, exit, and emergency routes is not installed. Understand 9 parameters. Scrap PPE does not have separate storage or disposal routine areas. Suffer from cobwebs and inadequate ventilation. Lighting is functional in some areas, but ventilation is insufficient. Under standardized 4 parameters, no SOPs are displayed in the store for cleaning, waste disposal, or material handling. No uniform signage format is followed. Under sustained 4 parameters, audit results are not posted on any notice board. No improvement suggestion system exists. What is important here is not just what failed, but that these failures are structural. They are not random or occasional. They reflect the absence of the system, not the absence of effort. The audit score tells a clear story. Let me go through each pillar. Sort series scored 3 out of 6, which is 50% grade C. Basic sorting is happening informally, but scrap zones are uncontrolled and not formally maintained. Set in order Ceton scored 10 out of 15, which is 67% grade B. This is the strongest pillar in the audit tracking. Rack labeling and zone identification are partially present, but floor markings and visual zones are missing. Shine scored 5 out of 9, which is 56% grade C. Cleaning happens, but it's reactive, not scheduled, not assigned to anyone formally. Standardized scored 2 out of 4, which is 50% grade C. SOPs are not displayed in the store. There is no formal visualized management system. Sustained score 2 out of 4, which is 50% grade C. No audit board, no suggestion system, no formal follow through. The overall score is 22 out of 38, 58% grade C moderate compliant. The key audit inference is this: basic 5S is initiated but not institutionalized. Sorting and arrangement need stronger enforcement. The immediate priorities are scrap zones, floor markings, emergency access, SOPs, and visual management. Fundamental practices must be strengthened before pursuing a higher audit score. These strengths and gaps together inform the corrective action plan that comes later in this presentation. What scores well should be replicated and standardized. What scores poorly needs targeted time-bound intervention. The industry survey collected 60 valid responses through Google Forms. The questionnaire comprised 17 Likert scale statements on a 1 to 5, open-ended question on challenges and suggestion, and 3 impact statement items. Let me explain the respondent profile because it directly affects the credibility of the finding. By designation, 42% of responses, which is 25 out of 60, came from store keepers and store in charge. These are the people who actually manage material in the store every day. 23% are site engineers and 20% are planning engineers. The data is not drawn from people with a who theorize about store. It is drawn from people who run them. By organization type, 87% are from contractor organization. Contractors are the primary entity responsible for FIS implementation on store. The dataset reflects field's reality, not client or consultant perspective. By project type, 50% of respondents work on high-rise residential project, 23% on high-rise commercial, and 13% on mixed use. This directly aligns with the scope of this study. By experience, 28% each have 5 to 10 years and 10 to 20 years of experience. Combined, 27% have under 5 years and 10 years, and 10% have over 20 years. The core data comes from mid-career practitioners with meaningful field insight. As I noted in my report, the majority of responses originate from store-level personnel who deal with daily material movements. Their ratings reflect operational realities, not theoretical ideas. This is what makes this dataset particularly valuable for the study. The pillar comparison table from the survey presents the clearest single picture of the situation in Indian high-rise construction sites store. Sort scored 3.78 out of 5, which is 75.76% grade B. Basic sorting is present, but scrap zone maintenance is inconsistent. Set in order scores 3.97 out of 5, which is 79.42%. The highest pillar material arrangement is the strongest area, but labeling is identified as the key weakness within it. Shine scored 3.40 out of 5, which is 68%. Grade B. Cleaning culture is reactive. It happens before inspections, not on a schedule. Standardized scored 2.28 out of 5, which is only 45.56%. Grade D. This is a critical gap. SOPs are virtually absent, scoring just 1.43 out of 5, the singlest lowest score in the entire survey. Sustain scored 2.12 out of 5, which is 42.34%. Grade D. No training, no audits, no management follow through. The weakest pillar. The overall score is 3.11 out of 5, 62.22%. Grade C. Moderate, functional but fragile. Improvements exist but are non institutionalized. The most important pattern I want to draw attention to is what I have called pillar decay. Short to set in order, to shine to sustain, to standardize, to sustain. The scores consistently decline as we move through the five pillars. This mirrors the classical 5S adoption failure curve seen in manufacturing literature. It tells us what that sites can initiate 5S at the operational level, sorting and arranging material. But without the governance layers, the standard procedures and sustained auditing, those initial improvements erode. That is exactly what we are seeing across these five projects. Short score 75.58% overall, which is grade B. Let me walk through the four parameters. The highest score within short is material disposal process at 86.3%, meaning respondents generally agree that there is some form of disposal process. Timely removal of scrap score 76.3%. However, scrap segregation scored only 74.7%, just below the 75% threshold, and scrap zone maintenance scored only 65%, clearly below threshold. The inference from this to below threshold score is sharp. Materials are often sorted, but the scrap zone itself becomes a dumping ground for materials that no one wants to formally reject. Sorting happens, but the designated space for sorted scrap is not managed. The solution is red tagging for items pending decision, category-wise scrap control for steel, timber, PPE, and general waste, and barricaded scrap zone with a weekly review cycle. Moving to set in order, we scored 79.42% overall, the strongest pillar in the study. Within this pillar, two parameters score very high: material accessibility at 85.7% and quick location of materials at 87%. These scores indicate that materials are broadly accessible and retrievable, but label storage scored only 69.7%, the key weakness within the strongest pillar, and this is where the critical insight lies. Materials are arranged but not consistently labeled. The store person knows where everything is, but no one else does. New engineers, subcontractor workers, and visiting staff cannot retrieve materials without assistance. This creates a manpower dependency that is fragile and unscalable. The corrective actions for labeling include a store level layout board at entry, color coded zones for cement, steel, formwork, MEP, finishing, and tools, diameter wise reinforcement labels, before tags on cement with receipt date and batch number, shadow boards for frequently used tools, and batch wise tile storage. The transformation from memory based to system based storage management begins with labeling. Shine scored 68%, while this grade is as a B. The internal distribution of scores reveals a structural problem. Store cleanliness scored 76.3%, acceptable. Tool maintenance scored 71%, moderate, but cleaning responsibility assignment scored only 56.7%, which means that in most sites nobody is formally assigned the responsibility of cleaning the store. That single parameter tells us everything: why no one owns cleanliness. Be- Cleaning becomes reactive. It happens informally only before a safety inspection or a client visit. There is no structured schedule, no daily routine, no end of shift reset. For high-rise projects specifically, this is a serious concern. Poor housekeeping block access increases safety risks, delay materials movement, and most critically, it undermines every other 5S improvement. You cannot sustain sort and set in order in a dirty, cluttered environment. The tool maintenance gap is also worth noting. Critical tools receive attention when they fail. Minor equipment is left unchecked and until breakdown or loss. No preventive maintenance is checklist is maintained. The corrective actions are recommended for certain for Shine are zone-wise housekeeping responsibility assignment for each material area. A daily housekeeping checklist signed by the storekeeper and verified by the site engineer, and an end shift of cleaning routine that resets store areas before the next work cycle. A preventive maintenance checklist for tools, cutting machine, and lifting accessories, and including housekeeping as a measurable item in the weekly 5S audit score. The cultural shift required is from cleaning is done when the store looks too bad to ignore to cleaning is done at the end of every shift by a named person, verified by a named engineer. Standardized score 45.56% grade D. This is the second lowest pillar and the one that arguably explains the failure of all other pillars. The three parameters tells a stark story. Assembly, availability, and implementation scored 1.43 out of 5. The single lowest score in the entire survey of 17 questions. The response distribution is damaging. 8 respondents strongly disagreed, 23 disagreed, 28 were neutral, effectively meaning most respondents either reject the existence of SOPs or have never seen one. Only one person agreed formal return procedure for material received, storage, issue, return and disposal are practically absent. Visual management, color coded zones, signage, floor marking, score 2.70 out of 5. These are not complex systems. Painted floor markings and printed zone boards require minimal investment, yet they are only partially implemented and inconsistently maintained. Documentation and record keeping score 2.68 out of 5. GRN records exist in some form but lack structure. There is no uniform format access team or project. The inference I want the jury to consider is that a store SOP is not a complex document. It does not require engineering expertise or specialized training to write. It requires someone to sit down and document how material should be received, inspected, stacked, issued, returned, disposed, and kept clean. But the document does not exist in almost any construction site store in this study. The store runs on tribal knowledge. It lives in people's head. When that person leaves, the system collapses. The corrective action include a concise store SOP covering all 8 function SOP flowchart displayed inside the store, not only in Office files, a uniform color coding system across all project types, standard templates for GRN, issue slips, stock registers, scrap disposal and tool issue records, and inspection checklist and monthly SOP compliance review by the PMC or a QA/QC team. Sustained scored 42.33%, the weakest pillar in this study, and I want to be precise about what this score reveals. It is not the people do not know about fire. It is that the culture and management structure do not support fires beyond its initial introduction. Worker training in fire scored 1.48 out of 5, 29.7%. 36 out of 60 respondents strongly disagreed that workers are trained in fires. This is the score closest to strongly disagree of all 17 questions. Workers and subcontractor teams are not formally oriented in 5S expectations. Without training, all habits return, not because workers are resistant, but because no alternative behavior has been taught. Regular audit conducted score 1.52 out of 5, 30.3%. 26 respondents strongly disagreed. No structure audit rhythm exists on any of the 5 sites. Deviation go undetected until they become major problems, blocked access, collapsed stacks, missing materials. Without any audit cycle, deviations are invisible for weeks. Management support and follow through scored 1.85 out of 5. 37%. 32 respondents strongly disagreed or at site level, what management does not review is not taken seriously. This is the cultural root of 5S failure. If the project manager does not walk into the store and ask for an audit scorecard, the store in charge does not prepare one. The root cause analysis is clear. 5S gets introduced during project kickoff. There may even be training session and a notice board, and then it is forgotten as the project lifecycle progresses. Without training, audits, and management commitment, 5S becomes a launch event, not a system. The corrective action monthly 5S 7S session for all store related personnel, inclusion in toolbox, talk during peak material movement, weekly 5S audits with scores tracked and displayed on a 5S board, assigned corrective action owners with target dates, recognized for the best maintained zone or subcontractor team, and 5S compliance as a parameter in subcontractor evaluation. This slide brings together three important dimensions of the survey: the impact of 5S, the challenges faced, and the suggestion offered by 560 industry practitioners. The impact findings are particularly important. Despite latest scoring only 42.33%, the perceived impact of 5S across material retrieval, waste reduction, and safety dimension average is approximately 71.4%. This is a significant and reassuring finding. It tells us that even partial or inconsistent 5S implementation generates measurable improvements on site. Think about what that means. Sites that have not fully implemented 5S, sites that score grade C or grade D, are still experiencing roughly 71% improvement in key operational areas. If full sustained 5S implementation were achieved, the impact would be sustainably higher. The other significant observation from the impact analysis is that experience level does not strongly differentiate 5S awareness. Even 10 to 20-year veteran rate situates poorly. This confirms that the problem is systemic and cultural. It is not about individual knowledge. Long-serving engineers have the knowledge, the system does not reinforce it. From the open-ended challenge analysis, space constraints are the most frequently cited barrier at 73%, followed by lack of awareness at 63%. Workforce resistance, rapid project pace, and lack of dedicated store personnel. From the respondent suggestion, training and awareness is the highest priority at 27.8% of mentions. Regular audits and inspection follows at 22.2%. Manpower and staffing at 16.7%. SOP development at 11.1%. Visual management, labels and signage at 11.1%, and space planning and digital tools at 11.1%. These suggestions directly align with what the data analysis found. The practitioners are telling us the same things the data is telling us. That element strengthens the validity of both the survey and the audit findings. The fundamental premise of this framework is that 5S cannot be a one-time initiative. It must follow the construction life cycle. It must evolve as the project evolves. The framework is structured across four project stages. At the pre-con or early stage, the focus is planning. Before major material inflow begins, store zones, movement routes, vertical access pathway, and rejection areas must be planned and mapped. Specific focus areas include cement stores, steel yard, formwork yard, scrap yard, tool room, chemical storage, and tower crane or material hoist access zone. During the structural execution zone stage, the focus is controlling bulk material flow. Steel should be stacked diameter-wise from day one. FIFO for cement should be enforced from the first delivery. Formwork accessories should return to marked zones. Weekly scrap disposal cycles must begin and not be suspended. During MEP and finishing state, the focus shifts to batch hour control and small item management. Tile batch, control sanitary fitting, storage electrical conduit tracks, plumbing bins, and adhesive and chemical segregation become the priority. Subcontractor coordination in the store area must be explicitly managed. At handover and demobilization, the focus is closure. Close unused stock, return reusable items to the client or the next project, dispose of scrap and document lessons learned from for future project kickoff. The framework also differentiates between residential and commercial high-rise projects. For residential projects above 120 meters, the emphasis is on standardizing the repeated flow cycle material flow, cement before reinforcement stacking by floor, formwork return, batch control, access typical flow. For commercial project, the emphasis is on managing material variety and multi-agency coordination, MEP storage, small item labeling, color-coded zone, subcontractor-wise accountability, and strict documentation for high-value material. The governance model has four layers. The store in charge handles daily labeling, FIFO, scrap segregation, and a housekeeping record. The site engineer does weekly walkthrough and corrective action notes. The planning, QA, QC, and safety team links bias with productivity and logistic data. And the PMC or project management reviews the monthly bias dashboards and tracks corrective action closure. The key monitoring indicators are material retrieval time, wasted percentage, blocked access incident, audit score trends, repeated non-conformities, corrective action closure time, and percentage of labeled storage location. This corrective action plan translates the audit findings and survey gaps directly into 8 site implementable actions. The first props of different types of stored together is a SARI and Ceton violations observed in projects 1 and 5. The actions are segregate props by size and type in designated racks and provide rack identification boards and show type, size, and quantitative. Maintain an inward-outward register and keep a minimum 1 meter aisle for FIFO compliance and easy removal. Second, my1 store with no passage and improper storage. A Ceton violation in project 1 and 5. Prepare a simple layout plan for the my1 store. Allocate fixed zones for panels, beams, pins, and accessories. Implement a no storage zone marking near entry and MEP access, and include access verification in the daily safety inspection. Third, MEP store access block. Sit-on violation in project 1. Clear access immediately. Maintain minimum required clearance. Paint a red boundary in front of the MEP store with a strict no stacking rule, and verify MEP access daily. Fourth, reinforcement scrap mixed with waste. Sit-on and SARI. Project 1. Create a separate scrap yard with category boards for steel binding wire and debris. Stack reinforcement scrap diameter wise with quantity tags and maintain a scrap reconciliation and disposal record. Fifth, tile storage without batch arrangement. Sit-on and equals to project 1 storage tile slot wise with batch number and installation flow level. Maintain for access clearance using palletized storage and prepare a tile stacking plan to prevent double handling and shade mismatch. 6. Sand and aggregate mixed with no zone definition. SARI, Ceton, and Secures to Project 1, 2, and 4 create separate marked areas for sand, 20 aggregate and 10 aggregate. Use partition walls or barricades. Define the final storage location before delivery to avoid double shifting. Seventh, mix debris waste at multiple locations. SARI and Sithor. Project 1 and 4 create a central waste collection yard with separate bins for concrete, tile, steel, and plastic. Implement daily housekeeping rounds before shift closure and assign a housekeeping supervisor for monitoring and sign off. 8. Reinforcement sizes stored together. SARI, Citon, and Sequestro. Project 1 and 3. Stack reinforcement by diameter, cutting length, and structured member, column, beam, or slab. Provide tags mentioning slab name and quantity per stack and maintain a cutting register for reconciliation. Let me bring this research together through 8 key findings. First, all 5 projects confirmed that initial logistic plans are well structured, but actual condition deviates significantly due to evolving site requirement. Not one project maintained its initial plan. Second, a consistent pattern was observed across all projects. Random stacking, blocked access, double handling, lack of labeling, and mixed material storage. These are not random site specific problems. They are systemic. Third, the audit score of 58% overall compliance, 22 out of 38 parameters identify scrap zones, floor markings, SOPs, and signages as the most critical immediate gaps. Fourth, the survey score of 62.21% grade C confirms pillar decay sought to set in order to shine and then a sharp drop to standardize and sustain. This is a classical 5S adoption failure pattern. Fifth, SOP availability scored 1.43 out of 5, the single lowest scoring item in the entire survey. Formal store procedures are virtually absent from Indian construction site store. Sixth, despite all these gaps, extremely 71% of respondents confirm improved material retrieval, waste reduction, and safety even under partial fire. The potential of full implementation is significantly high. 7. Space constraints at 73% and awareness at 63% are the twin primary barriers to full FIS adoption. 8. Citrus Q at 42.3% and Citrus 2 at 45.56% are not knowledge gaps, they are cultural and management commitment gaps. The final scorecard shows sort and set in order are operationally driven but need labeling. Shine is reactive and needs ownership assignment. Standardize is a critical systemic gap needing SOPs and sustain is a critical cultural gap needing audits and management commitment. The conclusion of this research is these construction site stores, though often overlooked in project planning, play a critical role in overall project performance. The adoption of 5S offers a practical, low cost, high impact solution. Even partial implementation yields 71% improvement in productivity, waste reduction, and safety. Shifting from reactive to systematic organization creates substantial impact when implemented with discipline and genuine management commitment and provides a strong foundation for lean construction in Indian high-rise projects. The framework, corrective actions, and governance model developed in this study can be directly applied by any project team on a high-rise site above 120 meters without waiting for expensive technology, large budgets, or complex systems. It requires discipline, a well-designed store, SOP, a weekly audit habit, and management that treats the store not as a secondary function but as a core operational asset. Thank you for your time.